I'm Austin, and this is Validated. Today I'm speaking with Kevin Bowers, the Chief Science Officer at Jump Trading. Kevin and his team at Jump are the brains behind Firedancer, an independent validator client for the Solana blockchain. If you're not quite sure what that means, you're not alone. We'll get into it in a minute. Here at Validated, we usually focus on big ideas in crypto, conversations steeped in broad themes with takeaways for everyone in the space, regardless of your preferred chain, regardless of your level of expertise. This episode is a little different. In fact, it's not really a crypto episode at all. It's more of a computer science episode that unfolds like a hero's journey into the world of high-performance computing. Kevin is the protagonist, and time after time, his call to adventure is, can we make this computer go faster? As you'll see, Kevin is in many ways a computer science iconoclast. After a long exposition of his unconventional career trajectory, he gets into the process of building Firedancer and what it means for the Solana community. If you're inclined to listen to this episode, you probably are already aware of why having a second independent validator client for Solana is so significant. But this is a point that we don't explicitly touch on in the episode, so I'd like to spend a moment addressing this. Validator clients are the actual software subsystems that blockchains run on. Every computer around the world validating blocks for Solana or any other blockchain is running a validator client. Today, every network except Ethereum and Bitcoin has a single validator client, one version of the software that everyone runs, no matter if the network has 75 validators or thousands. But this can cause big problems when something goes wrong. In fact, Ethereum's multiple validator clients is the only reason the network survived two major incidents in the last few weeks. But this episode really isn't about building a validator client. It's about the 1% of computer science focused on making things as fast and efficient as possible. The kind of fast where the amount of time it takes electricity to get from one part of the chip to another is meaningful, and just how different this is from the kind of software engineering 99% of us are used to. If you haven't heard our last episode with David Hoffman of Bankless, I encourage you to go back and listen to it. These two episodes highlight some of the most fundamental differences between Ethereum and Solana in terms of how they approach system architecture and software engineering. This is another big one, so settle in. Kevin Bowers, welcome to Validated.
Oh, thank you for having me.
I'm excited for you to be here. You are the most requested guest that we have gotten in the 6 months or so we've been doing the show. So
okay, that's kind of surreal from my perspective, but okay,
I know,
cool.
Right? Folks, I think in the Solana community and the blockchain world, they know you as the guy behind Firedancer, which is the new validator client that Jump is building. We'll get into what all those kind of words and details mean. But before we kind of get into the work that you're doing now and building on the Solana blockchain, I want to kind of start out with, like, how did you get into the space of high-performance computing? Walk us through a little bit of the journey from, college to where you are now today to then actually building an open source validator client for the Solana blockchain.
Okay, you asked me to start at college because it goes back further than
All right, let's go back to the beginning.
When I was really, really young, my dad worked as a programmer at a utility and would on Saturdays go into work and basically get me out of his mom's hair, would take me in and just basically sit me down and tell me to be over there in front of a terminal and not touch anything. But I did touch things. It was an old IBM mainframe, and I, spent a lot of time drawing ASCII art and whatnot on that computer system. And, you can imagine me as like a 5-year-old trying to read IBM systems manuals and not understanding what the heck it was. But what I knew I wanted to do was essentially make the computer do the kinds of things that were in some of the first movies that had computer graphics, which would be movies like Tron. Fast forward a little bit, there was a thing, again, through my dad's work, where they offered people to get discounts on buying a personal computer. And since they had a lot of deals with IBM, it was an IBM PC Junior. And the PC Junior was nominally PC compatible, but it really wasn't. It was missing a lot of features and whatnot. And that meant almost all the video games and whatnot I wanted to play didn't work. And so I started hacking the video games with things like, MS-DOS debug and so forth, and figuring out how to, make it do and it'll start to operate right. And so Had some success with that. And then, fast forward a little bit, when we start getting into college and so forth, I was initially interested in doing computer architecture and microchip design and things like that. That was my predominant area of interest. And took a year off school to kind of do back-to-back internships with Intel. That was mostly just because I wanted to do the co-op program, but they wouldn't let me do the co-op program. So they didn't have enough summers to do the co-op program. So I just took some time off and, worked for Intel doing some work there on the microchips. And one of the things I concluded when I was there was that Moore's Law was going to essentially run out of steam before my career was going to run out of steam. So I essentially pivoted into an area that was closer to maybe my native interest, which is essentially physics. I've always been a bit of a closet physicist there, and pivoted to study more signal processing electromagnetics. And so then when I went to grad school, I was doing a PhD thesis that was basically computational physics. And in doing that thesis, I needed to solve really big math problems on computers. But I was a grad student, I had no money, so I basically had crappy computing systems to work on, and I wanted to get my thesis done in a reasonable time frame, but I also had all this experience from when I was growing up, hacking on computers and making them solve problems really fast and, getting more out of them than people would kind of expect. And so the same thing essentially happened. I think the big thing there was I had a fellowship, and they had a little set aside saying, hey, if you're doing an experimental thesis, we have some money set aside so you can buy essentially equipment for doing your experiments to get your thesis done. Now, doing a computational thing, the closest thing would be like, well, you can go buy a computer with that. So essentially, I had fellowship money set aside for buying a fast computer. So doing what any self-respecting grad student would do, I bought what would be classified as a gaming rig for doing my PhD thesis at that time. This is also, I used to play a lot of video games, but I essentially stopped playing video games at that time because nothing really worked well on Linux at that time for video games. And I was doing all my thesis work in Linux. And so I was never, it was too much a hassle to reboot and go back into Windows or whatnot and dual boot. But had the system, and there's a dual core system. Now, this is back in the Pentium 3 era. The processors
good old days.
were cartridges that were on PCBs and so forth. And so I had a P3-800, two of those cartridges in it. It was a really badass system for the time, but it was basically being used for doing my thesis. But the big experience I had with that was, I got it and then was like, okay, I can now do my thesis twice as fast because I have two cores. And so I'm just staring at the computer, like yelling at it to go parallel. And it didn't do anything. And so I started looking at the various libraries around, what could I do? OpenMP was a thing at the time, but it was not open sourced. And, I didn't have any money for licenses for software like that. Your other libraries out there that really weren't designed for doing the kind of computing I wanted, but the closest I could find was MPI. And I found the books around MPI to be completely misleading. They would show you these examples like, okay, here's your problem and here's how you kind of write an MPI thing for it. And you read it, you think you understand it, then you go try to write your problem with it. And you discover that you didn't actually understand anything they were saying. And so it took, me about 2 years to get the conceptual mindset around how you actually properly design stuff for parallel and whatnot. A lot of that's very related to the kinds of same challenges that go on in a decentralized system. But the upshot of all of this is I wanted to get my thesis done fast. It was in the first .com boom. And so I wanted to graduate and get out. And so I was heavily incentivized to figure out how to get as much computing done on that system as possible and make all that stuff work. And I did. So at the end of the thesis, things went pretty well. Essentially in that era, if I kind of go from that era forward, if you look at the overall motif, I was trying to solve these really hard scientific problems that needed a lot of computing power, and I got really good at making computers solve them fast. And then as things progressed in my career, people cared very deeply about my abilities to make computers run fast and what I was specifically the scientific problems I was solving with them. So immediately after I got done with my thesis, essentially I was being encouraged to go down a path of being a professor at a large research institution. So I went off to Bell Labs, and there at Bell Labs, I was once again in this kind of area, theoretical, computational, using computers to solve problems really fast. But Bell Labs then immediately collapsed on me. It was a fairly traumatic first career experience. It also completely derailed me from that trajectory. So what happened next was I kind of concluded the private sector was really high risk and for the birds, and went off to Los Alamos, which was relevant to a lot of the thesis research I had been doing anyway. And there they, were very happy. Like I was doing supercomputing class problems on essentially this gaming rig that at the time literally was under the crib in the apartment we had out in Contra Costa. And so they're like, hey, here's a real supercomputer. Why don't you go do things with the real supercomputer? And so I started doing things with the real supercomputers there. And the big secret to all of this is everything is governed by this tyranny of Amdahl's law, where, you have these codes, they're written, they're really slow, they're not parallelized, but speeding up any one thing doesn't help. Like if you have, say, 10 things you're running in parallel and you speed up one of them, you don't get any faster. You speed up the second one, you don't get any faster. You speed up the third one, you don't get any faster. You speed up the fourth, fifth, sixth, you still don't get any faster. Eventually, you get to the ninth, you're still not any faster, but when you speed up the 10th thing, all of a sudden you get 1,000-fold faster. And things go through the roof. You have these hockey stick moments in kind of performance, and what you can do with these systems was qualitatively wrong and qualitatively, different from what people could do before. And so when I was there, due to various bureaucratic issues, I had kind of nothing to do for about the first 2 years. And so I just started writing some really, really fast codes for the kinds of problems that, were relevant to the work I was supposed to do there. In doing those, the big thing that you really care about is radically decentralizing the codes. You can't afford to have a central thing. And this is one of the conceptual things I was having with the MPI models in the past. You can't afford to, want to scale to 1 million cores, you can't have one core making a decision for all those million cores. You don't have the bandwidth to communicate the information to them. That one core doesn't then have enough information to make good decisions. That one core, even if it has good information to make those decisions with the bandwidth, does not have enough compute capacity to make those good decisions. And so when writing these codes, a lot of it was, how do I get rid of communications? How do I get the data flows optimized? How to make sure the information's in the right place, right time? The thing that I often kind of point out when you look at those systems, like one of the things, this actually occurred after I was at Los Alamos, but the code I was designed turned out to be really suitable for the world's first computer to break a petaflop. And I can go through the basic economics of it, but skimming through all of that, to make that system appear was a several $100 million exercise for all institutions involved. It only lasted about 3 years, and not because it broke or anything else like that. It's just the economics of these things are that after about 3 years, there's enough progress traditionally in the super chip designs and whatnot that you can just buy a new system, and it's cheaper to do that and operate that system than continue to run the old system. And so if you look at that and then you say, okay, I want to get the most out of the system. The system has, that one had on the order of 100,000 cores in it. You got 100,000 cores. You want to get things running well on that. And it cost you several $100 million to build. A lot of what people are taught is just absolutely wrong. Like everything they're taught is wrong. The entire economic, like you are in a regime where the machine time is more valuable than the people time. If you can get 10% more out of the system, it's easily worth tens of millions of dollars to you. You can afford to actually get down into the details of the hardware, get down into the details of how it operates. And the thing here, because of that Amdahl's law effect, it's not 10%. You get these hockey stick moments where you're able to do radically more with it. So in doing this, I was figuring out how do you radically decentralize, how do you optimize the data flows, how to get really fast. That became a pretty big deal. Shortly afterwards, the opportunity came up at a hedge fund that was interested in also exploring problems in computational physics, computational biochemistry. They wanted to design custom microchips for doing essentially protein folding calculations. Yeah. And oddly enough, mathematically, protein folding calculations look very similar to the kinds of calculations that I was doing my PhD thesis and doing at Los Alamos. And so, I was this weird person that had a background in chip design. I had a background in high performance simulations and parallelization and so forth. And so it was this kind of very unique opportunity. Did that, figured out, a lot of algorithms, parallelization, instruction set formats, all sorts of details about that. Had a good deal of success there. And, in that I was living in the New York area and was getting a little bit burned out on the New York area. And that's around the time Jump came along to me and said, hey, can you make our computers fast? And they're kind of secretive. So maybe in an act of hubris, my response was, I think so. But, that was kind of a guess. But beyond that, they were, in the Chicago area. And I was kind of looking forward to getting to a better work-life balance than I was having in the New York area. So I've been out here, and, it was I think, very fortunate time because the commodity stacks and what they were being designed to do, the way they were being optimized, they were at their limits. And there was a lot of slop in the trade.
Could you just define what we mean by the commodity stacks at the time?
So if you're at a trading firm, the trading firm, it's essentially buying server class hardware from big vendors, pizza boxes. They're putting them in racks and data centers. They're cabling them up with networking equipment. And the markets, the way they're structured is the market rewards heavily being first to bring new information to the market and make the market more efficient. If you're not making the market more efficient, the market will be either between indifferent to you or actively punish you. And so when you're doing this, the market doesn't care who makes the market more efficient. It's just a manifestation of the fact that if I want to go buy shares of a stock, I don't care who's selling them to me. A share is a share. Yeah. And so when you're setting up these systems, you are in this death match between all the other people in the market, and you want to be there faster. And this is not new. This is not even electronic trading. You can go back and you look at ye old-timey videos of people shouting at each other. You go back far enough, being a tall, loud person was a substantial competitive advantage at being able to trade in a market. Then as things moved towards, we're going to use phones and so forth, being able to dial fast became a competitive advantage. As things moved more towards, click trading kind of environments, things like that. Okay, some of those fast twitch gamer skills become a prioritized. But a lot of this stuff is heavily automatable. And so eventually those give away to, people talk a lot now about how AI is going to automate people and all of that. That's already happened in finance. So all of a sudden it's like, hey, I can replace a lot of this functionality with, fairly simple stacks, like, just write some things in Perl and Python and whatnot, and it will just do its job. But your competitors can do that, and your competitors can take the next step. The next step, they're going to rewrite it into C++ and whatnot. Well, you take the next step, they're going to go lower level, and they're going to do C and assembly language. They're going to take the next step and put FPGAs and ASIC. And so around the time I showed up, the commodity stacks on pizza boxes based on essentially kind of vanilla C++ style code were at their limits for what was doable. And things were starting to head bump against the speed of light limitations that are just pervasive everywhere, that are just terribly ignored by traditional areas in big technology and whatnot. Like the entire ethos that goes behind cloud computing is very much believes the speed of light is infinite, and it's just wrong. So as you're getting into these things, you're all of a sudden starting to replace the tech stack, but you're at a divergent point. The divergence being what is driving the vendors like an Intel, a vendor like a Dell or whatnot to develop their tech stack. They're essentially catering to the cloud computing market. They're catering to essentially lots of embarrassingly parallel jobs that aren't particularly latency critical. They want to have good power density. They want to have elasticity in their load and whatnot. And a lot of the features they're adding to their stack are very clever in that. And almost every single one is counterproductive for our needs. Mm-hmm. And so it's either we stick on commodity technology and then eventually get disrupted out of business, or we start developing our own technical stacks on top of that. And so that's where you start seeing the divergence. And, it was pretty fortuitous for me because, again, that, background of figuring out how to squeeze all the latency out of systems to get good scale, how to get right down to the metal and make things run very fast. And when you're also operating at the incredibly large scales, nothing works right. Debugging doesn't work right. You can't do printf style. It will destroy your log. Like nothing works. So a lot of those experiences were very useful. It's like, okay, the best solution in distributed systems is like design them so they're incredibly robust. And so that became very useful here. And we've been able to surf that down to the point where everything is right at the limits of speed of light. Everything is at the limits of Shannon information capacity for moving information across links. Now, this is the environment now where essentially Solana shows up and asks me, from at least my perspective, the same kind of question, which is that, like, we have this complicated distributed system that we've put together, and there's an old aphorism I like to say is that inside every complex system is a simple system that worked. And so, things get built on top of that, layered on top of that, but then looking at saying, hey, we really want to make this system a high performance, a reliable system, a well-documented system, and all of that. Well, this is just, from my perspective, something that I've done before, that we've at Jump done before in the trading context. I've done it in the high-performance computing for scientific computing context, and so on and so forth.
One of the things that really strikes me kind of about your background and just other conversations we've had previously on this stuff is the world pushes people to intense specialization nowadays. It's like, I'm going to be this one thing and this is the job I'm going to do. But like throughout your career, there's a whole thread of like, I wouldn't have been able to do this stuff in software if I didn't have this hardware background. And I wouldn't have been able to do this stuff with hardware if I didn't have this software background. And there's that very interdisciplinary nature while still in the high-performing computing environment that I think is just worth mentioning because so many people nowadays are forced to pick like, oh, I just work on this one small component of this much more complicated system. Have you found that to be sort of something you intentionally cultivated or you're just naturally curious?
That's a really insightful observation. If I go back to grad school, I had mentioned I had pivoted away from doing computer architecture to something a little bit more general and more kind of physicsy, but still within the engineering departments. So when I went off to grad school, it was pretty clear that I was being encouraged to study laser physics. And laser physics is very cool. There's a lot of stuff I love about laser physics. It's actually, oddly enough, been very useful here. But I didn't study laser physics for grad school. And so what happened? And it's exactly related to what you were saying. I showed up at grad school and I'm meeting with various advisors or potential advisors, and they're talking about, what kind of grants they have, what kind of areas of study, where are interesting problems, and what kind of things that they might want me to work on if I were to join their research group. So I would speak to people in the laser physics field, and I'd talk to somebody, and I'd be like, I'm really excited to meet you. You're the person who invented the distributed band feedback quaternary junction gallium arsenide indium phosphide doped laser that's cleaved on the 110 plane. Like that's a really cool device. It has all sorts of neat properties on it. I want to know a little bit more about it. How'd you get the inspiration for it? Whatever. And then in that discussion, at some point, I would be like, I was looking at the literature on this, and I saw that somebody had come up with the distributed band feedback laser that was a quaternary indium gallium arsenide junction fiber optic, but it was doped on the 111 plane for the cleaving of the thing. And the person just be like, nope, completely different device. Can't talk about that. Like, I don't know anything really about that device. And I'm like, as far as I could tell from my perspective as an outside, these were very, very similar devices. And what really worried me about that field when I was talking about is it seemed that the trajectory in that field was you become champion of a particular device. And so you are the person who is an expert on this kind of laser or this kind of photodiode. Like, one of the big challenges at the time was, how do you make a blue laser for, Blu-rays and other stuff like that with enough lifetime? And so there was a lot of stuff that was like, hey, you're going to be the blue laser guy. And so I'm like, okay, I mean, it sounds commercially relevant and all of that, but what if I want to do like a different color laser?
Sure.
Like, no, you're the blue laser guy. And so I didn't like that pigeonhole, and it really bothered me.
You were talking about decentralization before, and you were using it in a very different context, right? The idea of decentralization meaning like we're still talking about one centrally located compute system, but that the work of breaking up jobs so they can be done by 100,000 cores is a form of decentralization. So like moving forwards now to the work you're doing and your team is doing at Jump building Firedancer, which is this new validator client. Talk a little bit about how that is similar and different to the type of decentralization in high-performing computer systems, like supercomputer systems, and kind of what had to be relearned or learned differently now that you have to think about these things as being run anywhere in the world and not in these sort of tightly controlled production environments.
So I think when you say decentralization, in my mind, it's actually not different. There are some significant differences, but the one you're referring to actually in my mind just isn't. Because when you talk about things being within a data center as being centralized, from my point of view, it's still not centralized. and a lot of that, just look at a clock speed of a modern processor. You got 3 gigahertz. Okay, 3 gigahertz implies 300 picoseconds between clock cycles, and 300 picoseconds, light can move, ballpark 3 to 4 inches in air. If you actually go into the materials that these things are made out of, it's worse than that. But if you're actually looking at where are things from a physics perspective decentralized, you're already decentralized when you're talking about moving signals within a processor. You're already decentralized when you're talking about moving signals out to DRAM or some DIMMs that are on that box. Now, if I'm going even further, like saying I got a bunch of boxes in a rack and I'm going cabling to a top of rack switch or whatnot, I'm already radically decentralized. If I'm not designing up front with the notion that I need to be radically decentralized at that fine-grained level, I'm never going to get scale. I'm never going to get performance on those big systems. So what's different about the Jump environment? Well, before I worried about it within a data center. Like the big giant supercomputer was still in a big giant data center. Now it's like, well, Jump has the big giant supercomputer in a data center, but it also has data centers all over the world, and we got to get those data centers to communicate. And so there's an additional tier of decentralization that gets added on top of it. Now, I think with that tier of decentralization that's added on top of it, it's a lot more heterogeneous than what you're used to.
Yeah.
If you go buy a big supercomputer, effectively after all of the institutional, horse trading and whatnot has occurred, effectively big giant invoice goes out to the people who are going to build the system. Boxes of equipment show up, they get racked, they get placed in wherever they need to go, but everything is all same generation. The networks are all the same thing. It simplifies a lot of the system engineering problems because you can show up on a box and you pretty much know what that box is going to look like.
Yeah.
You have your network, you pretty much know what the network links are going to be like. Now, if you're doing stuff in the context like of finance on the jump side, you lose that. You might have that with an individual data center, the things that you control, but you don't actually control that much. If you want to go trade in an exchange, the exchange calls the shots. The exchange says, you're going to set it up this way with this kind of equipment. We've had surreal experiences where some exchanges, because they didn't seem to know much about how actual switches work, to rate limit people required you use 100 megabit NIC. And it was physically hard to find 100 megabit NICs. Like when you're used to buying 100 gigabit NICs and you're on phone calls with 100 gigabit NICs vendors, you're like, did you qualify this for 100 megabits? Like, please stop laughing at me. You want to go to their engineering staff on their side, like give them $10 and say, go to Best Buy and buy yourself at least a gigabit NIC or something. So when you're dealing with that, you have to deal with a lot more heterogeneous environment than you're used to.
Yeah.
And that creates a lot of challenges that I didn't have to deal with really before. I think another area which is strongly qualitatively different from before, if you just look how a big system at like the national labs gets administered, effectively you get a time slice. It lasts about 8 hours if you're going to use all the 8 hours. And a lot of times you're doing these runs that might use thousands and thousands, or maybe even in some cases millions of cores. And assembling all of that takes some time, and they also don't want you to monopolize those resources. And so what tends to happen is you get some carved out section of the system for about 8 hours, and then you run, and then you checkpoint your simulation, and then the next time you get an hour slice, you start up from the checkpoint and you run, and you eventually build up your simulation from all of that. But in that environment, no one cared, because you have an 8 hour time slice, no one really cared about a promptness to the run. So long as I could get my run spun up and running in, minutes, didn't really matter. So it's like, oh yeah, I'm going to read some files off a hard drive. Now, at the scale you're at, it's actually a bigger problem than I'm making it sound like. But no one really cared if the moment I hit enter to say, simulation, go start and run, if it started in a second or if it started in a microsecond afterwards. There was no need for promptness on that. And none of the hardware that you use off the shelf is designed for promptness like that. Now, you go to a market environment, it's the exact opposite. You have promptness requirements. When a signal comes in, you can't say, well, hey, wait, let me go spin off the cluster over here and think deeply about what this might mean for prices of other symbols, and I'll get back to you with a bunch of, suggested orders of things that are mispriced or whatever.
Right, because you're operating in a competitive environment.
Competitive environment. And it is competitive at nanosecond scale. Now, when you think nanosecond scale, think speed of light, foot per nanosecond. Like, nothing is designed right. Nothing is engineered right for that environment. You have to write your own stuff from scratch if you're doing it. And so this need for promptness created a whole bunch of technical challenges I never had to deal with. There's another aspect to it, and this is, I think the promptness need definitely applies in a Solana-like environment, although there's, I think, maybe more flavor of throughput, but a lot of that when you're dealing with shreds processing and whatnot. You don't want to be sitting around saying, hey, I can process a lot of shreds really, really fast, but give me a couple seconds here to spin up when you got a block time measured in 400 milliseconds. So I want to at least be kind of prompt.
Right.
But you have essentially the regulatory environment in which we operate is really, really strict. And you are in an environment where, okay, you got these systems, they're trading, 7 years hence, a regulator might be doing an inquiry and they say, hey, what were your strategies doing on this day at this point in time? How do you make this so that the systems are reliable, so that they're accountable, so that people can look at them? Now, if you run a big run on the big giant supercomputer, you make a bug in your code, you're probably going to have some people at NSF or Department of Energy or NASA or whatnot kind of irked that you waste that many million CPU hours on something that had a bug in it. But you're not going to have various regulatory agencies cracking down on you and being, sending you most unpleasant nasty grams and subpoenas and so forth, because you don't like if somebody shows up with a documentation request and your answer is, I forgot, that's not going to be a good day for you.
Right.
So when you're looking at putting these systems together, they need to operate in these extremely reliable kinds of contexts where you have lots of logging and accountability and transparency in them. So when things, have glitches or whatnot, you can figure out what's happening. You can minimize the amount of downtime, that you can figure out post-mortem what happened. And a lot of time that post-mortem could be years in the future. And so even the person doing the post-mortem may not be the person who wrote the code. And so how do you give all the context and whatnot? And those were challenges that didn't really apply. There's a little bit of a crisis in science in general around reproducibility, but it's existed in scientific computing for a while, which is you got some dusty deck code that's not being well maintained and there's no money for it, and the computers have evolved and somebody wants to reproduce something. Like, can you even get the code to compile? It's like we have that problem, but we have a much stiffer penalty if we get it wrong.
Yeah.
So, that's a challenge I never really had to deal with meaningfully until I was working here.
Yeah, that's interesting. I kind of love all the places we're going with this. One of the things you mentioned is like the work that's being done at somewhere like Jump now. It's like, oh, you have the freedom to explore FPGAs. You have the freedom to build application-specific integrated circuitry to like certain types of problems. When you're looking at something like a validator client for a network like Solana, even though it is in the world of blockchain high performant, in the world of maybe, the systems you work with, it's pretty slow performant. There are many problems that have to revolve on off-the-shelf hardware. And even within the off-the-shelf hardware space, like you can go buy easily you can buy a $90,000 server nowadays, right? But the requirements of something like a globally distributed blockchain mean just like that is not a viable instance to expect 2,000 people around the world to run. You talked about this a little bit, but modern software is designed to abstract away the hardware level. And so much of the work you're doing on Firedancer is about getting back down to that hardware level to eke out some of these optimizations. How do you balance the need to run on a wide range of hardware with these hardware-specific optimizations you're building into Firedancer?
That's a really good question. So there's a bunch of high-level observations to make there, and maybe a bunch of lower-level observations. But we're very aware if we show up and say, like, here is the most bespoke system that only the 4 richest kings of Europe can afford, completely defeats the point of the project.
Yeah.
And so as you've noticed, like on the demos, I was actually surprised after the demo at Breakpoint, people were complaining to me, why didn't you run it on fancy hardware? And I'm like, because the point of this is to run it on the most vanilla pizza box we could possibly find on that. One of the things that you alluded to there was the abstractions. It's not so much that we're getting rid of the abstractions, it's that everything has been abstracted incredibly badly. Like the way the abstractions that people are operating in, and they don't even realize this, they are actually actively dissuaded by this, by the way they're taught, by the various economic incentives. In a lot of cases, it makes sense, what they're being taught in the economic incentives, but in these distributed systems and these high-performance systems, basically regimes where machine time is more valuable than people time, everything is backwards. And the big thing here is, like, you look at that, like, really vanilla system, people are only getting a fraction of a percent of what's possible out of the systems. People are so divorced from the reality of what these systems can do that there is lots and lots of headroom, even without going into the fancy systems, to give a lot more performance improvement.
Talk a little bit about that. When you say that there's a lot of work that's not being done that could be done, like what causes that? Where do you see this unutilized power in just traditional systems today?
So I think the big thing here is that the mindset people have, like this really comes down to languages, that languages make compute look difficult and they make data motion look easy.
Yes.
So I have an array in my code, I have a float star A. It's very easy for me to say A bracket I, and then I think, oh, look, how cheap that is. And it's a mental model that goes back to that PC I was talking about. Okay, in that thing, you could have a zero weight state memory. Why do you have cache? You don't need cache. You have a zero weight state memory. Everything is cheap. Your expensive thing is how many operations you do. You look at all the wisdom, high performance, and whatnot that's built up. It's all built up around this notion of like, well, try to minimize the number of operations you do. It's like, okay, that's fine. There's nothing wrong with that, particularly algorithmically. You don't want to use an n squared algorithm when there's an order n log n algorithm or so forth. But when you actually get beyond that, you actually look at where the cost is. you look at how expensive is it to move operations around. I think I might have presented this at Breakpoint. If not, I have a slide that I often present to show people this. But if you look at the time it just takes light to propagate around a DIM, and you look at how many floating point operations you could get done in the time it took light to propagate around a DIM, you're looking at 3 to 5 orders of magnitude. And that's before getting into all the layers of abstraction that make it even worse.
Right.
And so you have people that are writing their code thinking like, I'm going to minimize the number of floating point operations I do. And they're looking at, so they're doing things like, I'm going to create like a lot of pre-computed data in memory and access it all the time. Oh dear, no. It's like that is the worst possible thing you could do for performance. What you really want to do is sit down and think very deeply about data flow. Now, the thing about that is there's not really any languages that express data flow or allow me to express data flow or locality or concurrency well. There's one counterexample I have to that, which is CUDA. If you go look at a language like CUDA, they have the thread index, they have the block. They are exposing to the developer saying, hey, if you tell me, where things are at in their abstract machine model, but their abstract machine model is locality aware, that we can have the compiler do a pretty good job optimizing for it. And this is why CUDA, I believe, has taken off so dramatically in these areas of high-performance computing and machine learning and so forth, is because developers have wanted to be able to say to the compiler, it's here and that's there, and please, don't be dumb about it. But they don't have the ability to even express that. And then the tools don't try to express it. They try to present the model that we're still in this compute-limited regime when really we've been in a data flow-limited regime for decades, and there's this huge mismatch between the software. So if you go back to your kind of white box question, the pizza box kind of thing, I got a generic low-end box, but I designed correctly around data flow limitations. All of a sudden, you're not getting a fraction of percent out of that system. You're getting orders of magnitude out of that system. And then, if there's demand from the community, we could show people what you could really do when you take the gloves off and you're willing to get fancy on the networking and so forth. And that is actually part of the demonstrations we have planned for some of the things going forward.
So kind of scaling that concept up, right? When you're thinking about data flow as opposed to like a bunch of copy operations, right?
Yeah.
What does that mean in terms of like from an architectural perspective, how you're thinking through how systems in Firedancer are going to work differently than the existing Labs client?
So we started from the data flow right off the bat. And that's also been baked into the structure of like the milestones that we've been presenting. And that's how you really have to start any of these systems. And if you don't have a system like that, when it comes to a thing like Firedancer, a lot of our homework in advance was figuring out what is the data flow through the system. And then you just are going to go incrementally back to that Amdahl's law thing. We can't really leave any stone unturned. If we really want to get it to be at the next level of performance, we really have to streamline every single part of that data flow. Otherwise, you just end up where you started, but you spend a lot of time. You might still get the benefits of the documentation and the independent client, but we are as interested in getting to something at higher performance, not so much because of competition against the existing cryptocurrencies, as we come from traditional finance. We know what those systems look like, and we really want this to be competitive in those environments as well. And so as we're thinking about how you streamline all of this, that's a lot of the challenge on data flow. So yeah, to your question, that's really what the initial approach is.
So as someone who works in these sort of very high throughput and high performant traditional financial systems, you hear a lot of folks in crypto talk about like, oh, we're rebuilding finance on chain. We're trying to be competitive with these centralized exchanges. We're trying to, rebuild the financial system. I think conceptually that is easy to understand. But you were just talking there about the delta between what we see in traditional financial systems and what we see in blockchain.
Yeah.
Give us a sense of how far away those things are today from one another.
So the fact that we've, like you already alluded to, application integrated ASICs, specific integrated circuits, the FPGAs and whatnot, we didn't do it for fun. Like naturally, we're a trading firm. If we could get by without making these big investments in technology, we probably wouldn't make the big investments in technology. We made the big investments in technology because they're critical to survival. So if you put this together, a lot of this comes down to the basic market dynamics. This is also something kind of talked about.
But sorry, just like, are we talking like 1,000x? Are we talking like 7 orders of magnitude?
I think it depends on which market you're looking at, and it's essentially a question of promptness. It's a question of a lot of it's related to discussions around layer 2s and layer 1s and different kind of distinctions. So I think the big things are the more zeros you tack on, the more problems that you can address with a particular level of technology. So if you tack on a 0 from where you're at, I think you become disruptive to a lot of applications that aren't the highest performing applications in finance, but that's okay. You tack on another 0 or 2 more zeros on that, then you're actually getting competitive with, a lot of the traditional kind of areas around that. If you put that in our perspective, we're looking at saying, okay, you got something that's in the tens of thousands of transactions per second. It's interesting for this class of applications, but it probably doesn't eliminate the need for centralized exchanges or whatnot, or at least a prompt centralized exchange. Now, if you tack on some more zeros, then you can start saying, well, now it's actually starting to get pretty interesting. Now, an interesting thing for me, and this is, I think, from my personal motivation in the project, is I'm not sure how far you can go. I know from the discussion about the existing commodity class boxes and so forth, there's a lot of room for improvement from where things are at today. But at some point, we're going to hit speed of light limits. In fact, a lot of this, I think, is already head bumping at speed of light limits in some indirect kind of ways. And then you get some interesting tensions between how might one evolve the chain, how might one integrate with other kinds of solutions on that chain, or other things to essentially break away from various bottlenecks that might exist on the network. And when I say network, I'm saying it the way I natively think of network. I'm saying it in terms of the actual physical cables that carry the data around the world, because we've had to do a lot of engineering of things like that. And I think there is generally a lack of awareness because of all these layers of abstraction. People have kind of just viewed that as a solved problem, and it's not. It's actually a very hard problem. There's a lot of neat things that go on in there. I think another trend we notice here, and this is something that I think Jump brings to the table that is fairly unique, but we see this from both the crypto communities and the big tech communities, that they radically underestimate the sophistication of the technology that goes on within finance. But this competitive dynamic really has pushed things to competitive at the nanosecond kind of level. And so I see results, to give a concrete example, a lot of colleagues I worked with at Shaw, subsequently when I worked on TPU, I see very neat results coming out of Google with things like AlphaGo. And they'll show these things like, oh, we got our deep learning neural network with 37 layers and 1 trillion parameters that we're training with our large language model and our all these other things, and it's all very cool. And look, it can make an inference in a millisecond, and that's incredible. And I'm like, a millisecond is 6 orders of magnitude away from being competitive in modern markets. And so it's I would love to be able to use all that technology, but I need to knock a bunch of zeros off it before it actually makes a dent over in those areas. And so if you look at what's this trend from starting off from the people shouting at each other in the pits to the technological state that we're at right now, you just have computers shouting at each other with network protocols. As you're getting into that regime, what you're really trying to do is get all the intelligence of a human down at those timescales, operating at those timescales, and no one's even contemplating that problem or even thinking there's an economic demand. So a very common thing that happens when we interact with, we've gotten the thing about the Solana project, Solana's already the fastest. Why are you so focused on making it faster? And I'm like, because I'm not worried about that. I'm worried about the competition over there. That's the competition you want to pay attention to.
I want to pivot here and talk about the project management side of Firedancer. When you're building another validator client, in order for it to have any real value, it can't be built on the same dependency tree that the existing client is built on. You're building from the ground up, in a new language, on a new stack. In the case of an actively evolving network like Solana, as opposed to something like Bitcoin where the protocol spec doesn't change, what's your approach to building when you don't know that end state? For example, you started work on Firedancer before local fee markets had shipped.
Yeah, it's hard. A lot of what we have to do on the traditional side of Jump has been likened to essentially replacing the jet of a jet engine while it's flying. You might well know exactly what your technical solution needs to look like.
A Dyson sphere is theoretically very easy to build.
Yeah. And so you can just say, hey, if everyone would just stop working for the next 6 months, we're going to go away and cloister ourselves in an ivy tower, and we're going to come out with this brilliant thing that exactly does the right thing and is totally engineered right and everything else. Well, you can't do that in traditional Jump. You might know where you want to get to, but you don't have that luxury because that's opportunity cost. While you're idle and waiting to build your new gleaming tech stack, Your competitors are out there. They're, actually running, they're trading, they're establishing market share. They're, beating the pants off you. So you don't have that luxury of just saying everyone stop, go away. In fact, it's worse than what I'm describing, because in lots of markets, you have a regulatory obligation to trade. And so like, if you just go away, the regulators be like, hey, you're supposed to be here. That's not cool. So I think it's a similar environment here. Solana is not alone. There's a lot of other competing things in the ecosystem. You just say, hey, everyone, stop. We're going to go away. We're going to come back with a shiny new thing. Then your competitors will innovate on top of that. People will, fork the existing code, continue to run. You'll, be in an environment where that doesn't work. So you have to do the same process of upgrading something while it's still running. Like the way it often happens traditionally is you'll have a, quantitative trader. They'll come up with some neat machine learning technique to apply to find opportunities other people missed in the market, but they're not experts in HPC. They don't know low-level networking or anything else. And so you'll look at what they've done quantitatively. They'll come up with something which essentially looks like some Python code that, or maybe some kind of quasi DSL, domain-specific language they whipped up for representing how they want to compute things and make inferences about the market or whatever else. But then, that doesn't run well. It's not, it's just some, half-baked interpreted language. You go try to put that in the market, it will be eaten alive by everybody else. So then you say, okay, what do we got to do on that? Well, it might initially make some money, especially if no one's thought of that opportunity before, but it's not going to make money for long. And so you want to be running that while you're upgrading it and evolving it at the same time. So a lot of the approach that we took is centered around the data flow. We just basically start, where does the signal come in? Put the existing code base up on jacks, rip out all the stuff below it, and then put in a new thing on that, lower down the existing code on that, make sure it still works. You didn't break anything. You got a faster layer there. You can see that with like the milestones we've done, the stuff we already demonstrated at Breakpoint, where we're starting at the networking layer and saying, okay, we're gonna get the networking layer really fast. And then after you do that, say, okay, we're gonna do the next layer. What's the next layer in the Solana case? We're going to take the runtime, put that up on jacks, take the account DB, put that up on jacks, and slowly extract that out as an individual component and engineer it, then lower it back down. Now, while we're doing this, the existing code base is evolving, but since we're not doing this in isolation from that, if there's a breaking change, existing code break, it will also break what our work is in our environment, and at least force us to respond to that, react to that, either by updating our stuff internally or, participating in the community by saying, hey, here are things that we've observed, here are things that we want to see happen that might improve your protocol in the future as you guys are evolving this. But it is a very tricky process, and it consists of both technical aspects, as you noted, but also people management aspects to it as well.
It's funny because like from the Solana core contributor community as well, this is a new thing for us. Like historically, there has been one validator client. It has been built by a fairly small group of engineers with lots of feedback from folks in the ecosystem. And those engineers work at different companies, but fundamentally they were working on one version of the thing. And so it's really, it's been a very interesting process here at the foundation, because we're kind of like a little bit of a coordinating layer between a lot of this work to sort of, figure out.
We were very worried the culture shock you were going to go through when all of a sudden, you have an idea and you just can't, implement it.
It's good culture shock, right? I mean, one of the really, I think, interesting things about the Solana culture is it's one that values moving quickly. And that is why the network is where it is today. But that's also why the network has had some of the uptime issues that it has had today.
Yeah.
No one ever wants to grow up until you're forced to by the type of engineering that you want to do, right? Like, it's what you're saying before. Like, if Jump didn't have to invest millions and millions of dollars in custom hardware and you and your entire team, they wouldn't do it, right? But these sorts of like forced learning is the best kind of learning to sort of mature and grow up an ecosystem and a product. Yeah.
Complete agreement.
It's very interesting to see. So, there's a few things that we kind of like touched on that I kind of want to like get into kind of in the last chunk here. One of them is this philosophy difference between complete abstraction of cloud systems and the sort of core by core addressing work that you are trying to do. If you kind of roll back, like, do you think, largely speaking, most of software has gone wrong somewhere and folks are not really doing it correctly now? Or just the type of work that like true professional applications, like the world you work in, requires something very different than the consumer applications of like a Zoom and, Slack and those kind of companies? Or are we losing something in the abstraction of modern software engineering?
I think there's a bunch of areas where things have gone wrong. But going wrong is going to be a matter of perspective. And there are two features that I'm going to say that are, almost heretical compared to what most goes on in software engineering.
Let's do it.
So I'm more than happy for people to say to me, I'm the weird one. I'm used to that. So one, I've already alluded to, but it's really in this domain and in the extremes of high performance computing domains I talked about before, there's an economic feature that doesn't exist in other areas. And that economic feature is that machine time is more valuable than people time.
Yeah.
And it's not because people aren't valuable, it's because the machines are processing data that's, so important or is, such constrained that, like, if I look at the machine at Los Alamos, if I get 10% more out of the machine, it's tens of millions of dollars. You know what? You can hire some pretty good software engineers and say, make it really fast at that level. Now, they're going to break all the rules that they were taught. Like they were taught premature optimization is the root of all evil. That's completely false. You don't do that. You have those ANDO laws bottleneck, that computer science decision paralysis. That's all wrong. So you're going to break all the rules. And you're going to get down in there, but it's worth it to you. Now, if you're in some other regime where it's like, I got something that's handling some web server requests. It needs to be human to real time. It needs to have elastic demand and all. These are the kinds of things that we see cloud design for. It makes sense. You also look at it from the design of a lot of startups. Somebody gets hired out of school, go to a startup. They, have a year of runway. They need to have for their next round of venture capital, their Google killer application, ready to go. What they're going to do is say, hey, it's more important for us with our limited developer time to cram the most out of developers, and any sins that we make in doing that, we just lie to ourselves and say, when we're a big successful company, we'll go back and we'll fix all that.
And no one ever goes back and fixes it.
Yeah, no one ever goes back to fix it. That's where you have the simple system that worked that becomes the complex system that is really tough to maintain. But you look at that; those economic they're real, they apply. But when I'm answering this, it doesn't apply here. Just I have that Python code that's really slow in the market, but is really clever. It doesn't matter because it's still really slow. And if I just buy 10 servers to do it 10 times, I'm slow 10 times. And I found a really clever way to lose money faster. So the traditional wisdoms don't apply. It didn't apply on the big machines at National Lab because the limited lifetime of the machine and the cost and how divorced things were. Another feature that goes on here, and this is very much related to the speed of light things, is at the end of the day, unless you make some really glaring engineering errors, which probably happen more than they should, but you can buy your way out of the throughput problem. I don't got enough throughput.
Yeah.
I can write a bigger check and buy more servers, and I can get more throughput. No matter how clever you are, no matter how big your wallet is, I can't buy a better latency. There's not some, gold package speed of light that I can get for Mother Nature to fix those kind of problems.
It's funny. There's this old adage that, like, a friend of mine used to work for Etsy and worked in the observability team for their infrastructure there. And they had this whole thing, which is like, if you can't solve the problem by throwing more hardware at it, you haven't solved scaling. And it's really interesting that, like, at web scale, that might be true. But at the level of work you're doing, it's like, no. Like, every computer we add adds 15 feet. And that means it adds X number of nanoseconds, and that becomes a problem.
Yeah. And then we're dead. Like I want to have the entire hyperscale data center fit in an area about the size of a basketball. Okay, no one makes that. If it's going to be made, I'm going to have to make it. Well, fortunately, we have a background and stuff like that, so that's not as ludicrous as it might sound. But it's clearly not being driven by what's being catered to by the existing kind of vendors and whatnot. Like I do think there's been such a divorce of reality, what the systems are capable of and whatnot, that they've gone overboard. It's not the only area where there are issues. Like that one, I can at least understand the economic dynamics. I think the other ones, there are deeper conceptual issues. Like I think there was a big mistake in how memory subsystems on CPU architectures have conflated the notion of virtualization and memory protection. I want protection. I want virtualization. I do not want my protection by virtualization. Almost all the pain that I deal with in coding up large systems is not figuring out how to be clever. It's the fact that these systems try to sandbox everything, but the whole point of these systems is to interact with the world. And so then when you're actually trying to get them to interact with the world safely, you're fighting with these operating system models, these language models, these machine models that just basically say you're in this, sandbox that starts at 0 and goes to 2 to the 64th, and it's just like an infinite tape Turing machine, and just count your ops and it will be fast. It's like everything about that is wrong. And it's deeply ingrained into how people think about languages and how they think about these. And like I mentioned, the only counterexample I have is CUDA, but CUDA is a major ingredient to NVIDIA's success here. They're the first place that actually said, hey, maybe it's a good idea to let people know locality is a thing. And then when the developers have the tools to express that, they do. And then all of a sudden, they're able to do things that aren't possible.
It's interesting that CUDA is the first place you can think of that's actually doing this, because in some ways, that's probably the least risky place to do that in an entire computer. Right?
Oh, I don't think CUDA's perfect. But
oh no, but it's interesting that they were willing to drop the protections down on, like, if something goes wrong on the GPU, like, we can kind of shrug it off, right? Like, if you overwrite the wrong piece of thing in active memory, like, you've completely crashed your computer. And I think it's really interesting that that's the place where some of those barriers started to come down.
Yeah, I could see the economic motivations that did it.
Yeah.
I think CUDA has the greatest hello world in the mankind. The way it looks to me is like going back to me as a grad student buying my gaming rig. This is pre-GPUs. Yeah. But I could just imagine me if it was a decade later and I'm buying that gaming rig and I could buy a decent NVIDIA card at that time. What does it look like? Well, this also informs some of the philosophy you can maybe see in some of the development of Firedancer as well. So it's not entirely irrelevant to the conversation. But I do it from the perspective of maybe somebody who's in a kind of corporate environment here, which is, the proverbial clueless manager. They're reading some industry trade magazine, and it basically says, GPUs are going to eat your lunch. You better have a plan for GPUs. And so they go tap one of their developers and say, hey, everyone says GPUs are really important. We need to have a plan for our GPU kind of thing. And then the developer gets really excited because their boss just asked them to go buy a gaming rig for work. And so they go buy a gaming rig for work. They go to the CUDA Zone developer website. At the CUDA Zone developer website, they have a completely non-judgmental thing where it's like, oh, you are running Ubuntu? Great. You're running RHEL? Great. You're running CentOS? You're running Windows 98 SE? Awesome. Here's all the platforms. It's very much related to your, we don't want to force people to be on any particular platform. It's bespoke. We want to have those properties where if you have some hardware that's barely functional, you can probably compile and get things to run on it. Maybe not run well, but you can probably get it to work. And so they're able to download it. They get it set up. Doesn't matter what they were running, whatever, preferences they have. And then they go and they look at the user manual, the getting started guide or whatever. The getting started guide, the first thing they showed you, and this has always happened to me, whenever somebody would show me the new language du jour, the first question I would ask them is, okay, that language looks pretty cool. Show me how to write a dense matrix multiply that hits machine performance. Not because all my problems look like dense matrix multiplies, but it will give me a good idea what features I can use in the language to actually get the most bang for the buck out of the hardware, because that's really important in the areas where I work. And anytime I'd ask that question, maybe a little bit of a gross analogy, but it would be people would act like I passed gas loudly in the room. And they'd just be kind of like, well, you wouldn't use this language for that. Like, it was beyond the pale. Somebody actually cares about using their hardware that they spent a lot of money to build. So I'd be like, okay, but if I can't actually get good performance out of this, this language is a toy. It's like, a safety scissors. It's not actually going to be usable for anything production that I need to use it on. So maybe it helps you, but it doesn't help me. So the thing here, what is the first example in this getting started guide? The first example is here's the 3-line nested loop on Intel for dense matrix multiply. So immediately I'm like, oh, I'm paying attention. So they go and they run that, and it spits out some number of gigaflops and so forth. And it's a bit of an unfair comparison.
Sure.
If that you really know what you're doing, you can do all fancy threading stuff. You can do all sorts of SIMD stuff and cache blocking and strip binding and pipeline, whatever. There's a billion and one tricks. But on CUDA's defense on that though is like, but most developers don't know how to do that, don't want to take the effort to do that. They write the 3-line loop. It's going to be reflective of what people actually see in the real world.
Yep.
And so then the next thing is like, hey, just put these additional little triple brackets around some things, and then go run it. Then all of a sudden the thing spits out a teraflop. And this, takes a good afternoon to do. It's not a big effort. And so the boss steps by and, says, hey, how's that GPU pilot project going? And the developer's really excited. The developer is like, oh, I did it. I got 2 orders of magnitude speed up overnight. This is totally great. And the boss is excited. The boss goes to their senior management and says, this is the greatest thing in the world. We're going to be able to, drink all the milkshakes of our competitors by doing a GPU. Invoices start going out the door, and everyone missed the hard part of GPU programming. Which is all the data choreography, the data flow, all the other stuff. It's the greatest hello world in the world. I think they've made tens of billions of dollars off that hello world.
Yes.
And so I'm always kind of cognizant of those things, about looking at those things. But to me, it's a power of the fact that modern languages and so forth have become so divorced from reality that somebody comes out. And the first time I read CUDA, I was trying to think, what's a thread? And my mental models Intel, and knowing something about architecture, eventually I realized what was going on is you're writing vector code from the perspective of the lane of the vector, and it's this radically more powerful conceptual model, and they've exposed it in their language, and I was able to vectorize stuff in ways that I would not have thought possible in Intel. Actually, they are possible in Intel, but Intel doesn't help you because they don't got the tooling. And so as you're going through all of this, like, oh, this is incredible. And having these conceptual models that let you think about the system the right way. And so I look at the existing languages, the way the protection models are set up, the way the virtualization models are set up. They are set up to emulate a machine that has not existed since the 1970s. And people are coding to that mental model.
Yep.
And everything is wrong. And they get a really subpar result. When they get a really subpar result, they have Amdahl's bottlenecks all over the place. And so then they just throw money at it, and hopefully they can weak scale and make the problem go away.
Have you thought of building your own language?
Yes. That's a really hard problem.
Yeah.
My background's not compiler theory and language. I have had to patch compiler bugs and whatnot in the past, but so I at least know enough to be dangerous there. I also know enough to know that's a really hard problem. And so I would love it if I could, just do one myself, and had the time to do one myself, I would. And I think that would be a big benefit to computing. I don't have any good examples. I think CUDA's the closest thing I can find right now that is kind of practical. I'm more than happy if somebody shows up at the end of the podcast and says, Kevin, you're totally out of date on all the neat stuff in computer science. And they give me 10 different languages that already do this. And, if I'm just totally ignorant here, I would love to know languages, because I really don't like coding in languages that have a complete mismatch between the paradigm of what the language is presenting and what I want to do. People have often talked about like Rust versus C and all of that. Like I don't like either. I want to be able to express my data flow constraints. I want to express my concurrency. I want to do it in a way where I get good results out of it. And you could maybe ask the question, why not CUDA? Well, CUDA actually, since you're talking about the sandbox, the kind of like over off the side of the GPU, there's a lot of features in CUDA that are pretty particular to how GPUs and CPUs historically interfaced that aren't there. And so I'm limping along in the languages that exist today. So
love it. Why are you not building Firedancer to make use of GPUs?
Well, we could. I'm not opposed to it either.
Oh, sure.
I think the big thing with GPUs, and this has been a problem from day one. In fact, a lot of stuff we can't make as much GPUs internally as we might want. And a lot of that comes down to trade-offs between throughput and promptness. GPUs are very well set up. If you look at their kind of model, they come from pixel shaders and OpenGL and whatnot. And you could see why there is this notion of here's a vector, but the vector actually can be like an array or maybe even a tensor-like quantity. And it needs to be dynamically sized because somebody might be running at 1080p for their resolution. So they want to have their array type be 1920 by 1080. Somebody else is running 4K. They want their type. So it meant a lot for them to put in some notion of here are these abstractions of a vector, but we're going to abstract it right so we can map it onto the hardware very tightly. Now, the underlying hardware, there's like a 32 wide SIMD that's going on, and they're being very clever on how they go about doing that and hiding those details from you. But then think about it from a perspective. And I've been raising this. I built my first GPU cluster back in want to say 2008. And I noticed this problem at the time. And this was a problem I had on the codes, like I was working at places like D.E. Shaw. Let me put some numbers around it. I'll use the D.E. Shaw example, but they will apply just as well in a finance example. If you want to do a protein folding simulation and you're doing it brute force, and so I can go into lots of digressions about tricks you might do. But if you're doing it brute force, you can basically say hydrogen bonds vibrate at about a femtosecond. So it kind of means your timestamp needs to be around a femtosecond. But biologically interesting things like protein interacting with the medicine takes about a millisecond, maybe more, maybe seconds. But you're looking at 12 orders of magnitude gulf between the timestamp and actually interesting stuff. which kind of implies a brute force simulation needs to do 1 trillion time steps. Okay, so you have this really nasty sequential dependency that's going forward. Now, if you want to get that done to be interesting to somebody, I need to do the 1 trillion time steps in a time which is like measured in days to weeks. Because if it's measured in months to years, no one's going to bother. And so that just sets a limit saying, I need to do a timestamp in so many microseconds. So I do a timestamp in so many microseconds, cool. Now you look and say, okay, within that time step, I have a budget of so many microseconds, and I need to do a ton of computational pipelines. And so one might be computing the strength of the forces between these atoms, one might be pushing particles around, whatever. Now, this actually isn't all that different, really high level from finance. Market data signal comes in, there might be 1,000 different things I want to compute on that, and so forth. And I want to respond really fast, so it's actually more relevant than it might appear at the surface. So I look at that and I say, okay, I might want to run 60 pipelines on my state of my system, kind of like, GPU shader passes in an OpenGL kind of context. But I need to get everything done in a few microseconds. Otherwise, it's going to take too long to run the simulation. Or if I do something similar, I want to run 60 different kinds of various machine learning-ish kind of evaluations on all of this. But I want to get it done in sub-microsecond, because if not, I'm dead in the market. So, okay, cool. Enter a GPU. GPUs, tons of parallelism, great concurrency, totally awesome. How long does it take me to spin up a thread block with 32 and just, one, like the minimum size? Basically say hi to a GPU and have it return and said hello back. At the 2008, it took me about 4.5 microseconds to do it. I couldn't, it wasn't worthwhile.
Fascinating.
And so I can't use this. Now you look at the underlying technology and you say, why does it take me 4.5 microseconds? And the answer you get is, this is great. This is incredibly fast. And their perspective is, hey, we're running at 60 hertz frame rate, and you want to do your 60 passes, and this is orders of magnitude faster than you need for your 60 passes on your shader pipeline. This is totally awesome. And so it was like, okay, but I actually want to do strong scaling parallel stuff, and it's over before I've even said hi. And then you go into the details of it, and you say, okay, why is it actually 4.5? Because I could interface with a network intercard faster. This is not that different from interfacing with a network card across PCI Express. And it's just they don't really see the incentive, because a lot of their application space, be it the traditional graphics applications or the machine learning, which is just pure throughput dominated, they don't care. Now, there are niches, not just finance, but there are niches like the high performance computing area I was coming from, where people have been poking at them with a stick. And you can see evolution in that area, things like GPU Direct and other ways of doing connectivity and so forth. But none of that's really caught up. Now, if you then ask, why not use it for Firedancer? I'm totally fine with using it for Firedancer. But, it runs afoul of a couple things that you already brought up before. So the first thing that you'd come in and you'd say, okay, if the only way to get it tightly coupled enough is for me to run the most bespoke GPU, and it has to be using GPU Direct and custom cabling and all sorts of other stuff, then there's going to be a community adoption problem. And it's going to be that really expensive system. You're buying the high-end branded parts and all the other kind of stuff. It's not so great. Now, another regime, though, you might look at, you might say, well, you don't have to worry about that so much. Just, don't go too far. Almost anyone who runs these is probably going to already have a fairly decent GPU in their system. And then if you go a little bit broader beyond the kind of CUDAs, and you throw in the AMDs and you throw in the integrated GPUs on Intel, you could also throw those into the mix. And like even an integrated GPU on Intel, that might have the ability to do some of this stuff faster. But a lot of this is, have they actually exposed the hardware well enough for us to do that in a meaningful sense? And that's kind of a crapshoot. You might get it, you might not. But then so ignore all those. Just say, okay, I'm not going to do anything special with the driver stack. I'm not going to do anything special with fancy hardware. Can I still use a GPU? The answer is, yeah, I probably could, but it's a lot more complicated a software design, because effectively I need to build up a big enough batch that I can send over the system to amortize those overheads that are too large on the existing GPU systems. And so the flip side is, well, if I can just get this running fast enough in a streaming context on an individual core, that I don't have to write the more complicated system, and I can keep it simpler that way. Now, where we're currently at in performance, I could see a regime And it's probably not the regime we live in today, but I could see a regime like coming up where you could imagine, things are deployed, everything is perfect, where you hit a limit where you say, hey, we're kind of running out of steam of what's being done on CPUs. And though we know how to do stuff very efficiently on FPGAs for a lot of this, I already alluded to some of the demos and whatnot that we have planned for that. FPGAs are rare. We've been targeting the Amazon F1 class FPGA because those are, as far as general community is concerned, I think the most widely available thing that's out there. But if you go say that's still way more special than just some, mid-range graphics GPU that exists. You could see a regime like, well, you get to high enough network performance and all that, you might have the ability to form big enough batches and do clever tricks with persistent kernels and all sorts of other games you can play with GPUs to be able to start amortizing those overheads and then start deploying them. So day one, it's not been a top target, but it's definitely something we are well aware of the existence of and what we need to do about it if that time comes.
Well, Kevin Bowers, thank you so much for joining us today, spending all this time and going into detail here. This has been really fun.
Thank you for having me, and hopefully I wasn't too rambly on the responses.
Validated is produced by Ray Belli with help from Ross Cohen, Brandon Ector, Amira Valiani, and Ainsley Medford. Engineering by Tyler Morissette.